everyone, my name is Sara Hakim. I'm a researcher in Mohammed V University Higher School of Technology in Salé, Materials, Energy and Acoustic team. First of all, I thank you to give me the chance to participate in this international conference and to present my work titled Modeling of Atmospheric Dispersion of Pollutants Throughout the Building using a Lagrangian stochastic model, which is an important topic in field of environment. This project is a part of collaboration between our school and University Paris-Saclay. I will present to you the plan of our presentation. We have an introduction, modeling of atmospheric dispersion, numerical result, and finally a conclusion. Cloud of pollutants released into the atmosphere is subject to different processes, the main one being advection and turbulence diffusion. The combined effects of these two processes produce a turbulent dispersion phenomenon. Efficiency of turbulence dispersion differ according to the distance from the emission source, so we need to correctly model the effects of the different turbulence structure. To simulate the turbulence dispersion phenomena, we can use an atmospheric dispersion model. There are multiple models like Gaussian, Eulerian, and Lagrangian model. Several researchers are already done in this field. The most recent are that made by Bahlali. In her work, she adopts the Lagrangian stochastic model of CFD called Saturn in order to simulate the dispersion of pollutants around a building, taking into account atmospheric stratification. In our work, we will present a summary of all these studies in order to show the importance of this model. Let us now present our approach. We consider the hypothesis of stationarity dispersion. Involve the implementation of two calculations, continuous phase and the dispersed phase. The first calculation is used to calculate the dynamic fields by solving the Navier-Stokes equation. As a result of this calculation, we have the mean value of velocity, pressure, temperature, and turbulence. Based on the result of the first calculation, the second calculation is used to calculate the dispersion of pollutants using two types of models, Eulerian and Lagrangian model. For the Eulerian approach, the concentration spaces within the pre-calculated incompressible flow, we have the mean advection diffusion equation. To solve velocity and turbulence field, we can use the CFD Saturn-Rance model with classical K-epsilon or REG-epsilon closure adapted to the atmosphere. For the Lagrangian approach, the movement of each particle included in the flow described by UP is governed by the fundamental principle of dynamics, and we have the following equation. By using the Rance model of Saturn, we can just have the statistical mean value of US, so to obtain US, that means to close the equation, it is necessary to produce a stochastic differential equation modeling the evolution of US, which make it possible to reconstitute the effect of turbulence. The interest of using Lagrangian model. The Eulerian model is enabled to reproduce near-field behavior, but the Lagrangian model that discriminates the two different diffusion regions. Let us now present the SLM model, the model for US. To reconstruct the turbulence effect, we need to develop a Lagrangian stochastic model. That's mean to refer in the PFD method. One of these methods is the SLM as presented in this equation. The reason of using the SLM, it has a very simple form and the pressure gradient term is clearly visible. It is rigorous and ensures full consistency with the mean Navier-Stokes and Reynolds equation with Rota's closure. For the numerical result, we showing the validation of the SLM model if we consider an homogeneous turbulence with an obstacle baseline within a boundary layer, and we choose to use the REG-epsilon model with Rota's closure. The mean particle volume fraction is shown in this figure. To show the importance of pressure gradient term, we will do not take in account the pressure gradient term, and mean particle volume fraction is shown in this figure. As we can see, we have an accumulation of particles. To showing the importance of modeling the flow with the R(-epsilon) model, we can model it now by K(-epsilon) model. As we can see, we have also an accumulation of particles. Based on the analytical solution, we say that the two approaches are almost the same performance near to the source, but when moving away from the source, the Lagrangian one is much better. The objective of this work is to present the adaptation of the Lagrangian stochastic model of CFD code Saturn in order to simulate atmospheric dispersion. Here we choose to present a very efficient tool for our problem is the SLM. As perspective, we will try to re-implement this model under code Saturn, then develop it and apply it to a Moroccan industrial site. Thank you for your attention.